Hello, welcome to Biomedical Ultrasound, Fundamentals of Imaging and Micromachine Transducers. I'm Professor Carla Mercado Shaker from the Department of Biological Sciences and Engineering at IIT Gandhinagar, and today I'll give you an overview and an introduction of ultrasound imaging. So let's talk just a brief history of ultrasound. How did ultrasound develop into the technology it is today? So we'll start with the early 1800s, wherein Jean Colladin determined the speed of sound through water using an underwater bell. Subsequently, Lord Rayleigh published a written work on theory of sound which delves into the mathematical foundations of acoustic waves. And then in late 1800s, the piezoelectric effect was discovered by the Curie brothers, which placed the foundation in the development of ultrasound transducers. Thereafter, in World War I in the early 1900s, sonar was developed. Sonar is the sound navigation and ranging system, which utilizes hydrophones to be able to detect sound underwater. Now, this was a technology that was used to detect submarines underwater to detect where the enemies are. And subsequently, in World War II, in the 1940s, pulse echo radar was developed. And many of the fundamentals in pulse echo radar are currently used for ultrasound imaging. Also in the 1940s, Dr. Carl Dusek, a physician, demonstrated for the first time the clinical utility of ultrasound by imaging brain tumors. So this was quite exciting. And subsequently, more experts such as George Lugward characterized speeds of sound waves in various soft tissues, especially using animals. And in the 1980s, this delved into more widespread use of ultrasound as well as the development of various ultrasound imaging modes to be able to image tissues. I'd also like to invite you to also look into several of these references that delved more deeper into the history of ultrasound. I talked about the piezoelectric effect and how is this useful in ultrasound imaging. So the piezoelectric effect is fundamental in the production of ultrasound. What it is it utilizes the effect within crystalline materials such as quartz to generate a potential difference when it is responded to in response to a strain. Subsequently, these materials can produce a strain in response to an applied voltage. So if you have an ultrasound system, typically that consists of electronic instrumentation that will then send an ultrasound signal to a piezoelectric element. And that element will then vibrate and produce an ultrasound to the subsequent medium that it is giving the ultrasound to. So a piezoelectric can either generate or receive sound wave by a principle known as reciprocity. Now, what is ultrasound? Ultrasound is a wave, and a wave is any disturbance or variation that propagates through a medium. Now, in ultrasound imaging, the medium that we're looking into is a fluid. So, ultrasound is a mechanical or an acoustic pressure wave over which encompasses frequencies that are above the human range of hearing. So, this is over 20 kilohertz. In ultrasound imaging, a common imaging mode is called brightness mode imaging or B mode imaging, and typically those images are produced in some grayscale pixels, and what it represents is the backscattered ultrasound that is produced to image tissue reflectivity. So how much of the ultrasound is going back to the transducer detector. In diagnostic imaging frequencies, we utilized about 2 to 15 megahertz in the clinical imaging range. But as you can see here, diagnostic ultrasound also goes down into the hundreds of kilohertz range. And this is typically used for therapeutic applications, such as inducing some bioeffect known as cavitation, or as well as heating, known as thermal ablation. So the therapeutic effect range goes from 200 kilohertz all the way up to 1 megahertz. And beyond 15 megahertz, we now delve into imaging smaller structures as we increase the frequency of ultrasound. Now, this delves into intravascular or even small animal imaging for preclinical studies. Here are some examples of the ultrasound imaging systems that are used today. So here's just a typical a scenario of what an ultrasound imaging procedure looks like, wherein you have a patient lying down and you have a sonographer that then holds a transducer, which can be used to image the inner body of the patient. And the ultrasound machine also looks something like this with a monitor and a keyboard that can have some knobs that can allow the parameters of ultrasound to change depending on how the sonographer would like to view the ultrasound image. On the top right, here are some examples of ultrasound transducers that are currently in use. On the left, we have a linear array probe, as well as two curved array probes here. Depending on the type of probe you use, depends on the type of application of ultrasound imaging. So later on, as we go delve more into ultrasound imaging systems, we'll look into how these transducers are developed and the physics behind them. We also have here what a mobile scanner looks like. So ultrasound is a portable imaging modality that you can take with you everywhere. And nowadays, there are ultrasound technologies wherein you can hold them by the hand. So you can mount a transducer connected to a phone and be able to visualize the inside of the body using this handheld portable system. So this is very convenient. And in the bottom right here, this is an example of an ultrasound, a brightness mode or B mode image of the a liver, which you can see here, and a right kidney right here. There are several advantages of ultrasound imaging and how this technology has become widespread use in the clinic today. First, ultrasound is very fast, can image very fast, more than 50 frames per second. There are more high-end systems now that can even allow you to image thousands of frames per second. And later on, we'll talk about examples of some of these technologies. Also, ultrasound is relatively inexpensive compared to the other imaging modalities. It's also safe because it does not involve ionizing radiation and it doesn't require you to cut open a patient to look into it, so it's fairly non-invasive. And ultrasound is pretty good at depicting soft tissue structures, especially with moving structures. For example, in ultrasound Doppler imaging, you can use this type of mode to be able to detect flow of red blood cells in the blood. And so this allows the structures to be viewed in real time. Ultrasound, because of the frequencies that we use, it also has good sub-millimeter spatial resolution. So as you increase the frequency, the spatial resolution of images can increase all the way up to the spatial resolution can enable you to image down to about hundreds of microns inside the tissue. But of course, there are some trade-offs with penetration depth, which we will discuss later on. Also, as ultrasound is a real-time imaging modalities, it also allows for short acquisition time, meaning an ultrasound scan can take as little as 2 minutes. And typically, depending on what the sonographer would like to see, can go up to several minutes, but it doesn't take that long. So it's pretty convenient. And due to the compact form factor of an ultrasound system, it is quite portable and can be used in many regions around the world, especially in the rural areas. Ultrasound imaging does have some limitations. For one thing, the images can have low contrast. Sometimes different structures in the tissue can appear similar in the ultrasound image. Also, since the transducer is relatively small compared to other imaging modalities such as CT or MR, there can be a limited field of view. Therefore, the sonographer would need to move the transducer at different regions to have a good view of the imaging region. Sometimes it's also difficult to interpret structures. There's some structures in the tissues that can appear the same in ultrasound, so that makes it quite challenging. Also, ultrasound is operator dependent, meaning that depending on the sonographer's interest and how the image should be displayed, the sonographer might move transducer at different locations in the body. They can also, the probe placement can also be a factor. So therefore, there are other approaches in ultrasound that try to compensate for these operator dependencies. Also, ultrasound cannot typically image beyond air, such as unfilled bladder or lung, as well as bone. And this goes into the concept of acoustic impedance, which we'll discuss more in the later slides. Now, what are ultrasound waves? Here are two ultrasound waves that we typically use when we do ultrasound imaging. The first, which is more common, is called longitudinal wave. In this case, as you can see here, we have a wave that is moving in one direction from left to right. And here in red, we have a particle. So you can think of each of these black dots as particles or small tissue structures that the ultrasound is trying to interact with. So you see that these particles are moving from left to right, and it moves left to right the same direction as the wave. So this is the characteristic of a longitudinal wave. And you also notice that there are regions where the particles are much closer to each other relative to other regions where the particles are apart. So these regions where they come close to each other are called compression regions, and regions where they are apart from each other, it's called rarefaction regions. This is also another example of a type of wave which is also utilized in ultrasound imaging in terms of elastography, for instance. Now we'll talk about elastography in a subsequent lecture as well. Difference between longitudinal wave and shear wave. For one thing, you can observe here that the particles are moving up and down, that is perpendicular to the direction of the wave motion from left to right. So here, shear waves are also known as transverse waves based on the nature of their wave propagation. So we'll revisit shear waves again in a subsequent lecture when we talk about elastography. But now back to longitudinal waves. So typically, these longitudinal waves are formed based on generate some vibrations in the tissue. And you also have a detector on the other side, which is also a piezoelectric material. And what you can observe from that detector is a type of waveform that looks like this. Typically in ultrasound imaging, the waveform is of a sinusoidal form like this. And we usually view it as a function of time. So the amplitude of ultrasound is defined by its pressure right here. And the regions where there are high pressure, where the particles are close to each other, again, are called compression. And the particles that are moved apart, move away from each other, in terms of low pressure, it's called rarefaction. And here's just one example of a piston transducer here that excited the medium with just one pulse, so a single ultrasound pulse. And what you can observe from a detector is a signal that's similar to what is seen here. Now, in ultrasound imaging, you typically send pulses, short pulses, typically 1 or 2 cycles. So what I'm showing here is just an example of a single pulse. And this pulse can be characterized by several parameters, including one period. So I mentioned earlier that the single pulse, it can be a sinusoidal pulse. So one period corresponds to one cycle of this pulse here. And that's typically denoted as T here. And in ultrasound, because we image at megahertz frequencies, the time of the single pulse is usually around microseconds. So a period can be as small as ones of microseconds. Also, we notice that there are 2 cycles. So 2 cycles of the ultrasound pulse has a certain duration here, defined by its pulse duration. And one by the period of the pulse is known as the frequencies, and typically we use megahertz frequencies. So just looking into the units of frequencies that are used. So you know that 1 hertz is 1 cycle per second, 1 kilohertz, 1,000 cycles per second. In ultrasound imaging, we used over 1 megahertz, which is about 1,000,000 cycles per second. And in typical clinical applications such as transcutaneous ultrasound, where you're imaging through the skin and imaging organs inside the body, typically we use about 1 to 15 megahertz. When we talk about imaging the heart, echocardiography, which is widely used in the clinic today, about 1 to 7 megahertz is used. When we talk about imaging the eye, such as an ophthalmic ultrasound, Since we're imaging smaller structures, we need better spatial resolution. And these are more superficial structures, so higher frequencies are typically used beyond 10 megahertz. So later on, we will discuss the relationship between the frequency as well as the depth of penetration of ultrasound in the body and how it can impact spatial resolution and how it can also determine what kind of application of ultrasound you will use in the body. I've also discussed ultrasound imaging is not only one single pulse, but multiple pulses. So here I added two more pulses. We have a second pulse here and a third pulse here. And typically the pulsing of ultrasound is characterized by how often it's being sent. So pulse repetition period is a parameter that is used to the amount of time it takes for one pulse to come after the next. So it's typically in the microseconds range. And we look into the wavelength of ultrasound as well. So one cycle can be defined by one wavelength. And this wavelength parameter is denoted by the sound speed, in this case longitudinal sound speed, divided by the frequency of the sound. And these frequency time period relationship, you can also convert it as the speed of sound times the time period, and you get the wavelength. Similarly, sometimes in the literature, you can also see the term pulse repetition frequency. Now, this is PRF. It's just 1 divided by the pulse repetition period. And these are some parameters that you will typically see with regards to ultrasound imaging. Another parameter is called the duty cycle. And you will notice that in this pulse right here, I denoted the time that it takes for the pulse to be on, or the transmit on time. And since ultrasound imaging is typically a pulse echo type of imaging technique, so we'll discuss more about what pulse echo means. There will be a time where that echo of ultrasound needs to come back, right? So which means that a pulse that's going to the tissue should not be interacting with the ultrasound that is coming back to the tissue. So the transmit is off during this time right here. So here, this is the time with which the echoes of the ultrasound will be received back to the transducer. And what a duty cycle is, it's the on time of the transducer divided by the on time plus the off time. And the sum of these two is just the post repetition period. So it's typically multiplied by 100 as duty cycle is expressed as a percentage. And for imaging application, typically what is used is less than 1% duty cycle. There are also other applications of ultrasound, such as in therapy, that uses even beyond 1% duty cycle to induce some bioeffects in the tissue for therapeutic purposes. Now, there is a special relationship between time and space when you talk about ultrasound. And the factor that can allow you to convert from time and space, or distance and time, is the the longitudinal wave speed here. So for example, we discussed what the pulse duration is. So a wave has both a time component, that the pulse is described by the pulse duration, but as well as a distance component, a space component. And you can describe that pulse by a spatial pulse length. So this is that parameter. And the wavelength or the wavelength, the longitudinal sound speed is what converts between this time and space. So for example here, just a pictorial depiction of what is actually going on. In this y-axis, I have time, and it's defined by the period at different instances of time, okay, where t is one period. And you have here the x direction, which is the unit of space right here. So we have our pulse here that is as a function of space. And at another instance of time, let's say quarter of a period has passed, then this wave has moved into this direction. And then another instant of time has passed, then you can see that the wave is moving as well. And as you can see, as one period has passed, the uh, the wave has moved of a distance that is equivalent to one wavelength. You can see here, this is a one single front line. So this is just showing you and giving you an appreciation of how ultrasound wave has both time and space components. And later on, we'll delve more into the wave equation that includes both of these components in a mathematical formulation. We talked about sound speed, especially longitudinal sound speeds that are used in imaging. So another formulation of a sound speed is basically a characteristic of the medium, characteristic of the tissue. So as you can see here, tissues have different longitudinal sound speed, and it's a factor of the compressibility of the medium, which is also an inherent parameter of that tissue, as well as the density of the tissue. And just of note, one by the compressibility of the medium is an elastic parameter known as the bulk modulus. So there's some mechanical parameter that also is related to the sound speed. You can see here that different tissues have various longitudinal sound speed. Water, for instance, fresh water at 20 degrees has about 1482 meters per second. And since much of the body is mainly comprised of water, you can see how these sound speeds fall within the range that is centered within the water longitudinal sound speed. We have fat here that has a lower sound speed than water. And we have other hard tissues such as bone, because they're highly dense. They have a really high longitudinal sound speed all the way up to 4,000 meters per second. But with regards to soft tissues, what is set in diagnostic scanners is a longitudinal sound speed of 1540 meters per second, which is the average of all the soft tissues in the body. Now, how do we measure longitudinal sound speed? Actually, those that I have shown you earlier, most of the longitudinal sound speed I reported for tissues are actually empirically derived, meaning that we measure them through experiments. And here I show just a practical example of how to measure longitudinal sound speed of tissue. Now, what this is called is a through transmission setup. And what I'll describe are the different components of this setup and why it's called through transmission. So what we have here, typically ultrasound imaging experiments are done in a water tank environment, which mimics the soft tissues of the body, which is mainly water. And the water tank can be set to different temperatures. Depending on the temperature of the medium, the sound speed can also change. What we have here is a pulse generator that will excite a piezoelectric transducer. Now this will transduce or transmit an ultrasound signal that then propagates inside the water. In this case, we don't have a tissue sample, so the water is just propagating through, the wave is just propagating through the water. And then we have our detector here, a receiver, another piezoelectric transducer. It will receive the signal. Since ultrasound signals are typically small in amplitude, we typically need a preamplifier to heighten the voltage of that signal. And then that will be sent to a digital oscilloscope, digitize the signal into a computer where you will be analyzing the ultrasound signal. So we'll have another case where we then put in the tissue sample right here. And this tissue sample typically has a sound speed that is different from water. And so we do a similar experiment where we transduce or transmit an ultrasound wave, and that wave will pass through the tissue sample. There could also be some decrease in the amplitude of that ultrasound signal. We'll talk about attenuation in a subsequent lecture. So the ultrasound signal can get attenuated through the tissue, and then that can get received by another piezoelectric transducer here, which will then be digitized and sent to a computer for analysis. So this is called a through transmission setup because you're transmitting an ultrasound pulse through the tissue and receiving it with another transducer. And what here are just some examples of what the signal that you will find in an oscilloscope, for instance. So here you have an amplitude here, and this can be converted to a pressure later. It's a function of time here. What you'll observe is the pulse here will look like the pulse that has traveled through the water tank without the sample. And if you plot it against also the other signal that is received in the experiment with the sample, it will look like this. And you will find that it is slightly time shifted by duration of delta t right here. And you also notice that the signal amplitude will also decrease slightly due to acoustic attenuation through the tissue, which we'll describe more in a subsequent lecture. So this is the equation that you will use to estimate the longitudinal sound speed of a particular sample. It is a function of the longitudinal sound speed of water, which is CW here. And there's a nice resource from a journal in the 1950s that already tabulated all the temperatures and the longitudinal sound speed that was measured in fresh water. So one can look at this resource to be able to obtain the longitudinal sound speed of water at a particular temperature. And in this equation, we also have the time difference, that difference in post arrival time with and without the sample that you would have measured using the signal. And then that is divided by the thickness of the sample. And what is typically done to get the thickness of the sample is a measurement using a ruler or a caliper. And this you will have to measure empirically. So hope this lecture gives you a brief overview and good introduction of ultrasound. We have discussed the history of ultrasound. We've also discussed the concept of piezoelectricity and how ultrasound is generated by different piezoelectric materials. We've also looked into the advantages and the limitations of ultrasound imaging and dove into the different types of waves that are frequently assessed in ultrasound, such as longitudinal and shear wave, which we'll describe more in later lecture. We also looked into some pulse parameters that can characterize an ultrasound pulse. For instance, we looked into period, frequency, pulse duration, and so forth. And longitudinal sound speed was discussed in different tissues. And I also gave a practical example of how to use an experimental setup to measure longitudinal sound speed of a material. So this ends the lecture for today. In the next lecture, we'll be discussing the wave equation.